Well, thank you very much. It's a great honor to be here. It's also a great pleasure. I came to Waterloo from Belgium exactly almost to the day 36 years ago to start on a PhD here, working with Ray McClanahan, who was my thesis advisor. Coming to Waterloo from the University of Brussels was like a breath of fresh air for many reasons. The professors were accessible, they were wonderful, they were not demigods sitting on Mount Olympus like the professors I had in Brussels. But there was also a fantastic group of fellow graduate students, and basically we learned as much from each other as we learned from the professors who taught us courses. I mean, this being said, and it doesn't matter if Ray is not here, I want to pay special homage to Ray McClanahan. Ray did for me something that I only understood the value of much, much, much later, which is that he shared his research program with me. Now you have to understand the research program for a scientist, for a mathematician, it's like your most prized possession that you keep in the bank vault, and because it's what is going to keep you going and motivated for many, many years to come. And Ray shared this with me very generously when I started here on my PhD. And what the ideas that he shared with me sort of stayed with me for the rest of my career and were at the root of some of the things that I have worked on and that I take some pride in. He also taught me something which is, I think, very important for students to always remember. Primo, that research should be fun. And you should always look at research as being a fun, enjoyable activity. That you should take joy and comfort in making progress in small steps. Small steps are things to be proud of. You should not be discouraged. And that you should, it should be an enjoyable, it's a noble activity, but it also should be enjoyable. And the fun element should never be taken out of it. You need to keep a positive attitude. Let me share a secret with you. 99.9% of the time, we're stuck. Everybody's stuck. Okay? If you're working, it's normal. But you should not be discouraged by that. So these are the things that Ray taught me and that I've kept with me. So I wanted to pay homage to him for this. Okay, so what I thought I was going to, I wanted to share with you. So, and I apologize for the handwritten sheets. I'm old enough to expect for there to be a blackboard. When I give a talk, when I realized there was not going to be a blackboard, I just scanned my handwritten notes. So I apologize for the fact that this is handwritten. What I wanted to do was to share with you a story that's known probably to a number of the people present in the audience today, but which has always fascinated me about the discovery of the field equations of gravitation by Einstein. And, I think it's fair to say that Einstein's general theory of relativity is one of the supreme achievements of the human mind. What could be more beautiful, first of all, than to think of gravitation as manifested as curvature of space-time, but it's not just only beautiful, it's got tremendous predictive value. I mean, gravitational waves, black holes, the Big Bang, all of this followed from a set of equations that Einstein arrived at on the basis of his genius and tremendous hard work as a scientist and physicist. What is less well known to the general public is that the great mathematician David Hilbert, with whom Einstein was corresponding and whom he visited, was also thinking about the problem of gravitation, a relativistic theory of gravitation, but from a very, very different perspective, which I would like to briefly describe for you today. And what's absolutely remarkable is that chronologically, the first paper to contain the correct set of equations describing the relativistic theory of gravitation was published by Hilbert and not by Einstein. It predates the publication of Einstein's paper by a few days. And they arrived at this through completely different paths, and I would like to describe this for you today because I find this duality quite fascinating, and I don't really understand why it should be true. So you know him, right? So this is a picture, I think, from 1921. So this is after he became very famous. Okay, so this is after the famous experiment of the solar eclipse with the bending of light rays. But if you look at the face, I find one's gaze, one's eyes reveal a lot about a human being. And there is something, an amazing sense of wonderment and marvel that emanates from that gaze. And in some sense, you can see he still had the fire burning in the belly and his heart was still beating fast when he thought about science, obviously. This is David Hilbert, a bit older than Einstein. So Einstein was born in 1879, Hilbert was born in 1862. Mathematicians are not as well known as physicists, but what's, I think, remarkable about Hilbert is that after Poincaré, who is referred to as being the last mathematician who has mastered the entire corpus of mathematics of his time, Hilbert, I think, came pretty close to that. So there is, maybe with the exception of topology, but maybe Peter can correct me on this, I don't think there is a branch of mathematics that Hilbert hasn't touched and had a profound impact on. Think of commutative algebra, think of number theory, think of analysis, think of geometry, think of partial differential equations. He's touched, everything he touched, he made new. He was really a universal mind, and he did for the mathematical community something which is extremely generous, because instead of just writing papers and publishing them, he also published problems. And there is a famous set of problems associated to Hilbert that he presented at the International Congress of Mathematicians in Paris, which are still keeping mathematicians busy to this day. And people who share problems rather than just sharing finished packaged results deserve a lot of admiration because they're very generous people. Okay. So, 1915 is when this set of equations was first published. These are known as the Einstein equations for the relativistic field of gravitation, a theory of gravitation. So the left-hand side is geometry, is curvature, and the right-hand side is matter radiation. My friend Demetrios Christodoulou has a beautiful way to refer to this. He refers to the left-hand side as marble and the right-hand side as wood. And, geometry, curvature, it's carved into marble. It stays. Wood decays. Even old cedar will eventually decay. But the two talk to each other through these equations. So I'll comment on these a bit more, but what's really remarkable is that these appeared simultaneously in papers by Einstein and Hilbert, as I said earlier, starting from very different premises. So the question is, how and why did this happen? That's what I want to talk about today. Okay, so a little bit of chronology. 1905, you all know the story. Einstein was a clerk, civil servant working in a patent office in Bern, Switzerland, and he came up with the revolutionary idea that space and time are really observer-dependent notions. But this observer-dependent notion of space and time would just apply to observers who are in uniform motion relative to each other. So they move at constant speed along straight lines. But it's good enough to account for all the phenomena governed by electromagnetism, electromagnetic waves, light. The special theory of relativity is completely compatible with that and works extraordinarily well, experimentally and theoretically. Problem is that if you think of gravitation, right, if an object is dropped in a gravitational field, it will be accelerated. And Einstein, soon after the publication of his paper on the special theory of relativity, started thinking about the way in which gravity could be incorporated into a relativistic theory. And he came up in 1907 with the so-called equivalence principle, so the idea of saying that uniformly accelerated observers and gravitational fields are the same thing. And he called it the happiest thoughts of his life. It's original German, because it's really a thought experiment that led him to that conclusion. Of course, it took a long time for this insight to turn into a set of workable mathematical equations. And pretty soon, Einstein realized that in order to make this work, he would have to use tools coming from a branch of mathematics called Riemannian geometry. Riemannian geometry is the generalization to higher dimensions of what you do when you study the intrinsic geometry of surfaces. So surfaces, not simply up to rigid motion in an ambient space, but surfaces that you can deform as long as you don't bend or twist them. So as long as you keep lengths and angles constant at corresponding points. And he started collaborating with a mathematician by the name of Marcel Grossman. And as a result of his discussions with Grossman, and Grossman was very punctilious, he just dealt with the mathematics, and Einstein dealt with the physical part of the theory. He came up with a set of field equations. Took a while, but in June of 1915, he published a paper in the Proceedings of the Prussian Academy of Sciences containing a set of equations which describe gravity in terms of a metric tensor, in terms of an object which is a higher dimensional analog of the metric geometry of a surface. Except that these were incorrect, but he didn't know why. Initially, he realized that they were incorrect after publishing the paper. So even Einstein was not infallible. But he didn't really know why, and he came up with all sorts of gimmicks to try to fix the problem. While he was working on this, so maybe this is on the previous page, I don't know if I mentioned this, but he lectured in Göttingen, where Hilbert was based, so at Hilbert's invitation, and he presented his incorrect set of field equations in Göttingen, where he visited at Hilbert's invitation. Okay. Independently of Einstein, Hilbert, on November 20th of 1915, submits a paper to a local journal based in Göttingen, which contains the correct equations. And observe the dates. This is November 20th. November 25th, Einstein presents, independently of Hilbert, the paper which contains the same correct equations. Well, Einstein was not so happy when he found out about this coincidence, and the relations were a bit clouded. In one of the biographies of Einstein that I read, there is a reference made to a letter that Einstein wrote to one of his friends, in which he essentially accuses Hilbert of having plagiarized him. Okay. However, things, I think, were worked out between them, because in December of 1915, so a little bit later, a month later, Einstein writes to Hilbert, and I quote from the letter, he says, "There has been between us something like a bad feeling. I once more think of you now with unclouded friendship." So what happened is that Hilbert acknowledged the priority of Einstein in terms of coming up with the correct framework and with the correct ideas, even though the publication of his paper containing the actual equations predates that of Einstein by a few days. Okay, so in the rest of my talk, I have for 10 minutes left, I want to give you a glimpse of how Einstein, the path that Einstein followed, a glimpse of the path that Hilbert followed, and you'll see how they arrived at their conclusions. Okay, so this, take you back to your undergraduate courses. This is mass times acceleration equals force. If you have a force field which is conservative, if it derives from a potential, then you can write the equation in terms of the potential in this form. The mass, the inertial and gravitational masses are the same, they cancel out. And the potential is the gravitational potential generated by a mass distribution. And rho is a function that gives you the mass density as a function of spatial position. This is Poisson's equation, which relates the potential that determines the force field to the mass distribution. And so it's a second-order elliptic linear PDE. Okay. So the first thing that you want to do if you want a theory that treats all observers on the same footing is to try to rewrite these equations in geometric form. So what do? You introduce space-time coordinates like this. And lo and behold, you can rewrite these equations in purely geometric form. Don't worry about the details. These are like the equations of a straight line, but in a curved geometry. These are called the geodesic equations. These are the equations that govern curves that minimize arc length between 2 points. In Euclidean space, well, the curves that minimize arc length are the straight lines. In a curved space, well, you've got these funny gadgets here that reflect the fact that measure in a certain way that help measure what the curvature of space is. So these are what we call the geodesic equations for a torsion-free connection. And the curvature of this connection, so the curvature of this space-time continuum, is actually related to the Laplacian of V, which appears in my Poisson equation here. So Einstein knew, in fact, it was in the air, that something related to curvature of space-time should play the role of the gravitational potential. Except that the potential, instead of being just one function, would be a collection of functions describing the more complicated geometry of space-time. Okay. So curvature, it's a complicated story. Okay. It's complicated. But basically, curvature is a nonlinear, something that depends nonlinearly on second derivatives of these functions that describe the local geometry of space-time. When Grossman told him that curvature was nonlinear, he thought that Einstein would be upset. On the contrary, Einstein was very pleased that the theory was nonlinear because he knew that objects are affected by their own gravitational field. And this can only happen in a nonlinear theory where you can't superpose solutions. of a differential equation. So it had to be nonlinear. Einstein was pleased. He was happy about that. So it's a nonlinear mess. That's why the subject is complicated. But it's also why it's beautiful, because out of this nonlinear mess come out black holes and gravitational waves and the Big Bang and all of that stuff. Okay. So I promised you a link to Poisson's equation. So you take this big curvature guy. It sort of looks like a curl plus a commutator, for those of you who remember calculus. Curls measure rotation. So curvature measures the amount by which a vector rotates when you do parallel transport along a closed loop. So there has to be a curl somewhere in the expression of curvature. It's reasonable to expect. So you choose a special connection, and out of that special connection comes curvature, which is exactly the Laplacian of V. It's the left-hand side of Poisson's equation. It's the marble part of Poisson's equation. The wood is the mass distribution. Okay. So Poisson's equation I can rewrite in terms of one piece of the curvature. Okay. How do you do it in general? Well, problem was that Einstein didn't know what are known as the Bianchi identities. So curvature, as I mentioned to you, is this complicated nonlinear superposition of second derivatives of the space-time metric, but curvature is governed by some syzygies. It's governed by some identities. And if you don't know what you're doing, there is not a chance on Earth that you will figure out that curvature satisfies this. This is known as the Bianchi identity. Einstein didn't know the Bianchi identities. Hilbert did, and I will tell you why Hilbert knew the Bianchi identities in a moment. So he had the wrong equations because he was looking for something which will satisfy a conservation equation, will have zero divergence, constructed out of the space-time curvature. Well, the answer is that you need to take some funny combination of traces. Again, if you don't know, it's like throwing darts in the dark. You will never figure out what this is. But this is the object that you need. If you remember, this is my marble, my left-hand side in the general Einstein equations. And the Bianchi identities tell you that this has zero divergence. Einstein didn't know that. Okay, how did Hilbert know about this? Well, Hilbert's axiomatic approach was to posit that any physical theory should derive from what's called the variational principle. So whether it's electromagnetism, whether it's gravity, whether it's nuclear forces, whatever it is, there has to be a functional, so a map that assigns to the fields describing your physical process a number that's obtained by integrating a density. And whatever the solutions are of the equations that govern your physical phenomenon, those solutions must be such that the value of this functional is ideally minimized. Okay? At the very least, it should be like a critical point. So either a max or a min, or possibly a saddle point, but we don't like saddle points because they're unstable. Okay? So that's a branch of mathematics called the calculus of variations. When I was a student here, Ray McClanahan taught a course on the calculus of variations. It's a classical subject that goes back to Euler and Lagrange, and it's just extremely beautiful, complicated. In fact, one of Hilbert's problems, you could paraphrase as saying, put some order into the calculus of variations. Because you can start with a functional that's very nice, and the minimizers can be extremely irregular, even if the functional is nice. one of Hilbert's problems was to try to put order into this. So what do you do to find the equations that govern the critical points? Well, you do the first derivative test. This is called the Fréchet derivative. And what you obtain is a set of equations known as the Euler-Lagrange equations. I don't know if they're right here. So whatever phi is, it must satisfy nonlinear differential equation. If your density depends on first derivatives, this equation in general will involve second derivatives. The order is always doubled in general. Relativity is an exception to that, by the way. But I don't want to get into the details. Okay. Why is this good? Well, it's because these equations will automatically be invariant under changes of coordinates. Remember, this is one of the things that you're looking for when you try to generalize gravity to a relativistic theory that incorporates the equivalence principle. You want equations whose solutions will be the same or will be covariant whenever you change coordinates, and that will patch on overlaps of domains of coordinates. And this is very nice. The calculus of variation guarantees this for you. So it's a little exercise in doing the chain rule. If you make a change of variables like this, this Euler-Lagrange operator that I had written on the previous page, let me see. Here we go. This operator E alpha of L will transform homogeneously. So solutions in one coordinate system will automatically be solutions in any other coordinate system that overlaps with the original one. And the transformation law, if you're interested, it's given here. So it involves Jacobians, as nice as possible. So graphs of, that's what I wrote at the bottom, if you have a critical field, a critical point of the functional, they patch on overlaps. Okay, I'm almost done. For Hilbert, what's his field? Well, it's the space-time geometry. It's GIJs. What's the simplest density he can write down? Well, it must be a scalar density in order for this equation to be invariant. So he did the simplest possible thing. It's not unique, but he literally took the simplest scalar density available as a Lagrangian. And he did the calculation that I showed you at the bottom of this page. And he obtained, so this is the Lagrangian. And ta-da, he obtained exactly the Einstein tensor. This is textbook material. How did Hilbert know that this had zero divergence? How did he know that he could solve what was Einstein's stumbling block? Well, this is because of a beautiful theorem, which is due to Emmy Noether. So Emmy Noether is mostly known as an algebraist. She was a very distinguished algebraist. She was the daughter of a famous mathematician who worked in algebraic geometry by the name of Max Noether. And she was his immensely gifted daughter, who, because of the times when she was born at, was never made a professor, which is an absolute outrage. So even when she moved to North America, she was just a lecturer at Bryn Mawr College, even though, most colleagues she would have had would have been dwarfed by her genius and talent. Anyway, it's a different story. So she discovered a theorem which has nothing to do with her work in algebra, which says that any time you have one of these variational functionals which has symmetries, which doesn't change under the action of a transformation group, automatically you can write down a conservation identity from the knowledge of how the group acts. Here the group is very, very big. It's the full group of diffeomorphisms of the underlying manifold. The Bianchi identities, these mysterious identities, they arise just by applying Noether's theorem to the Lagrangian that Hilbert wrote down here. And the fact that the marble has zero divergence comes out of that. Okay? So, I'm almost done. Don't misinterpret what I'm trying to say. I'm not claiming that Hilbert is the one who discovered general relativity. No, he didn't discover it. This is really the brainchild of Einstein's genius. However, this story tells two interesting things, in my opinion. One is that by some, I hate to use the word mysterious in the university, but I have no other adjective to describe it. For some mysterious reasons, it can happen that the principles of simplicity and beauty applied to physical laws lead you to truths which are as close to being universal as Einstein's general theory of relativity. That's one example. It's not the only one, believe me. Those of you who know about antimatter and the Dirac equation, if you read what Dirac wrote about the way in which he discovered the Dirac equation, he was also guided by principles of mathematical simplicity and coherence and elegance. I don't know why, okay, it works, but you can't ignore it because I think it's there and it's an experimental fact, okay? And it's not just Einstein and Dirac, I mean, it's everywhere. The other thing which is very interesting is that, and this is mostly for the students, a few students here, don't worry about your mistakes, right? I mean, if Einstein was stuck and was making mistakes, he was stuck on this so between 1907 and late 1915, he worked on this until he literally got sick. Okay? So if he did that and kept going and kept his spirits up, don't get discouraged when you're working on research. I think that's the main thing. And finally, between honorable scientists, their priority disputes, typically get resolved. Not always, but often they get resolved. And in this case, between Einstein and Hilbert, as you can tell, within a month, it was sort of water under the bridge, and they were friends again. Okay, I'm done. Thank you.
Minutes. Would you be willing to take some questions?
I'd be delighted to, of course.
Questions from the crowd? Oh, we got a couple. Start down here.
Are you aware of any correspondence between Einstein and Hilbert
Yes.
that sort of addresses the cloud, sort of from, November through to the end of December?
The only thing that I am aware of, and which is quoted in every biography of Einstein that I've had the opportunity to read, is that little excerpt I quoted. So probably there was more, but it might have been lost simply. So the only thing I'm aware of is just that quote, which is indirect.
Yeah.
Seems like Poincaré, like he published the two parts, like special, Relativity 1905. That was partly flawed, but was before Einstein.
Absolutely. This is thank you for mentioning this. Yeah, so, the special theory of relativity is anchored, or can be understood, or can be anchored around the properties of Maxwell's equations and the symmetry properties of Maxwell's equations that govern the propagation of electromagnetic waves, that govern electromagnetic phenomena, and the whole algebra that underlies the special theory of relativity, which is really quite simple. It's linear algebra. All emerges from playing with Maxwell's equations, and you're absolutely right. So Henri Poincaré wrote a paper in which he reinterpreted or interpreted or gave this framework for understanding special relativity in 1905 through the prism of this group of transformations. That's absolutely true. I think Einstein was less happy with Poincaré than he was with Hilbert. So if you read the biographies, there are instances in which Einstein says that Poincaré understood nothing of relativity, even though he understood the mathematics, of course, in depth. But you're absolutely right. Yeah.
1905 paper, why didn't Einstein like, give proper credit to previous experiments like that, Marshall, like, you know, like all that? Like, why didn't he like give proper credit to it?
Mystery, we don't know. So there is a beautiful biography of Einstein written by Abraham Pais that I warmly recommend to you. The title is "Subtle is the Lord." It's a famous quote where Einstein said, you know, "Subtle is the Lord, but malicious he is not." And it's, if you go to, anyway, it's now in the mantelpiece of one of the chimneys in Fine Hall in Princeton. So Abraham Pais, who was close to Einstein, because he was a professor at the Institute for Advanced Study, once discussed this Poincaré paper. It's a paper published in the Rendiconti del Circolo Matematico di Palermo in this Sicilian journal, Mass Society journal. And so Einstein, it's hilarious, right? He says, "Oh, I've never seen that paper, or I don't remember seeing it." And Abraham Pais says, "Well, would you like to have a reprint of it? I have a reprint of that paper in my possession." And Einstein says, "Okay, sure." So Abraham Pais lends his reprint of the Poincaré's paper to Einstein. And after Einstein's death, this reprint had disappeared. So nobody was able to find it in his papers. So maybe there was a bit of a, angle mort, as we say in French. There was a blind spot in his memory about that. But clearly the relationship between Einstein and Poincaré was not of the same nature as what it was between Einstein and Hilbert.
Even the previous experiments, like he didn't reference any. I think like during in the late 19th century there were experiments.
Yeah.
He never.
Yeah, that's right.
Any other questions? Okay, barring none, we're gonna, first of all, Niky, thank you so much for coming from Montreal
My pleasure.
to join us for the day. We
Thanks.
do have a small gift
Oh, thank
on
you.
behalf of the faculty
Thank you very much.
for you.
Thanks a lot.
Please join me in welcoming or in thanking.
Thank you.
Cameron.